Let's say we have a car driving at a constant velocity. We can graph its movement with position on the y-axis and time on the x-axis. Taking any 2 points on this line, we can find the car's velocity, or average rate of change, by dividing the change in position, y, by the change in time, x. This will give us the line slope, or the average rate of change of this car. Since our car is moving at a constant velocity, the slope of our line is also constant. But what if our car wasn't moving constantly? What if it slowed down, stopped, then sped back up to the start? Well, then we would have something that looks like this. Now, you should be able to recognize this curve as a parabola. And on a parabola, we can actually find the rate of change pretty easily. We will take 2 points, point A and point B, and we will draw a line between them such that the line goes through both points. We have now formed a secant line to our graph, and if we find the slope of this line, we can find the velocity that our car had, on average, between times A and B. As a reminder, this is our average rate of change. But what if I want to find the velocity of our car at a single point? Let's say we pick point A. We can call this velocity at a single point the instantaneous rate of change, because it is happening at an instant. Well, an easy way to do that would be to move point B closer to point A, then move it a bit closer, and even closer, until our secant line is no longer a secant line but a tangent line, touching our parabola at just a single point, point A. We can find the slope of this tangent line using limits, because we can take our slope formula, the change in y over the change in x, which we can write as f of b minus f of a over b minus a, and take the limit of it as b approaches a, as b gets closer and closer to our point A. Then, we can make this even simpler. Let's define our b as a plus some h, an unknown value. Well, then we can rewrite our function for the slope of our tangent line, or our instantaneous rate of change, as m equals the limit of f of a plus h minus f of a over h, because the a's cancel out, as h approaches 0, since our difference between a and b is becoming non-existent. This is called a derivative. You'll often see it denoted as dy dx, or you might see something like this, which is f prime of x, or the derivative of f of x. Now we can apply this formula. First, let's take a car that is not moving. It is at a single position, we'll call it 5, so our f of x is going to be equal to 5. No matter what f of x we take, the value is 5, so we're getting 5 minus 5, which would be equal to 0. That's because our car is not moving, so its instantaneous rate of change at any point is just 0. If we take the derivative of any constant, we are always going to get 0. Now, we'll have a car moving at a constant speed, divided by f of x equals x. In this case, once we plug in our x for a, we can see that the x's will cancel out, so we will be left with h over h, or 1. So the derivative of x is just 1, which is our car's velocity here, and it will be the same all the way through. Now, we can go back to an earlier question we posed to ourselves. How can we find the instantaneous rate of a change of a car if its movement is akin to that of a parabola, which we'll define by f of x equals x squared? Well, using our new definition of a derivative, we can find out pretty easily. First, let's square x plus h, as this is our x and it functions as one unit. Then, we'll subtract x squared from it. If we expand x plus h squared, we get x squared plus 2xh plus h squared, from which we subtract x squared to be left with 2xh plus h squared over h, or 2x plus h. If we take the limit of this function as it approaches 0, we get that the derivative of f of x, f prime of x, is just 2x. We can do this with more complex movements of a car too. What if our car slowed down, then stopped and then sped up? We could probably graph this with the function of f of x equals x cubed, which we can apply to our derivative formula. So we have x plus h cubed, which expands out to x cubed plus 3x squared h plus 3xh squared plus h cubed, from which we subtract x cubed and divide by h, getting 3x squared plus 3xh plus h squared, which, if h approaches 0, is just 3x squared. So by now, you should be seeing a pattern. When we differentiate, we multiply the function by our current exponent, and then subtract 1 from our exponent. In calculus, this rule is called the power rule, where the derivative of x to the power of n is equal to nx to the power of n minus 1. If we use this to check our functions, we get that x is equal to 1 as x to the power of 0 is 1. The derivative of x squared will be 2x to the power of 2 minus 1, or 2x, and the derivative of x cubed will be 3x to the power of 3 minus 1, or 3x squared. It is also good to know that, during differentiation, constants factor out, and the derivative of a sum is the sum of the derivatives. Finally, note that these rules are not all-encompassing. What if we are trying to differentiate two functions that we are multiplying together or dividing? What if our function is a trigonometric function? What if we have one function nested in another? Calculus has differentiation rules for all of these, but we do not have time to cover them in this video.